Hello everyone, welcome to our channel OnlyPhysics JEE Grad. So in this video we'll be discussing JEE Advanced PYQs, JEE Advanced PYQs from the chapter Gravitation. This will be the second and the last video on this chapter. So topic are we are left with escape velocity and satellites, right? So there will be 21 questions. Last in the last video on the gravitation we have discussed 19 questions. So these will be last 21 questions. So let's start with our first question. So we have here, right. So in this question, there are two satellites, P and Q, are moving in different circular orbits around Earth of radius r. Perfect. The heights P and Q from the Earth's surface are HP and HQ. Okay. So we have two satellites. Let's say this is our Earth. This is the first, and this is the second. Okay. So we have this is the first path, just like this. So here, let's say we have our first satellite. This is so P and Q. Okay, let's say this is P, and let's say this is Q. Okay. Now the height of P from the surface is this. So this is R by 3, and let's say this is HQ. Okay. Now the gravity. Okay. So we have given GP by GQ. So how will you write GP? So GP will be uh, acceleration due to gravity on P satellite. So it will be plus G upon 1 plus D by R to the whole square, right? Or we can write this formula. You can write the formula directly. So what it will be? It will be simply G M by R plus H the whole square. This is of course mass of the Earth. So it will be Earth. Yes, so this is Earth. Now this is HP and we have given GQ. Of course, it is not given, the ratio is given. So it will be GME upon R plus HQ to the whole square, right? Okay, so let's divide both of them. So this will get cancelled. GP by GQ is 36 by 25. We will have R plus HQ to the whole square upon R plus HP. HP is R by 3 to the whole square, right? So if you take the under root, it will be we will be having 6 by 5 R plus HQ upon this will be 4R by 3, right? So let's just cross multiply. Okay, so this 3 will go up and we'll cross multiply them. So we will have 24R equals to 15R plus 15HQ, right? So what we have here is 24 minus 15. We will be having 9R upon 15 equals to HQ. So you can cancel out. You can divide it by 3, both numerator and denominator. So this will be 5. So we will have HQ equals to 3R by 5, right? So A will be the option. So quite easy question, right? Let's move on to our second question. Let's move on to our second question. So we have this one. Okay. So we have a rocket launch normal to the surface of the Earth away from the sun. So let's say this is our sun and this is our Earth, and a rocket is launched like this, okay, away from the sun, along the line joining the sun and Earth. Okay, perfect. Now the sun is 3 into 10 to the power 5 times heavier than the Earth. So if say this is mass of Earth, so we'll write it as 3 into 10 to the power 5 mass of Earth. This is mass of sun. and the radius of sun is 2.5 into 10 raised to power 4 radius of earth, right? Okay, the escape velocity from the gravitational field is 11.2. The minimum velocity required for this rocket to leave the sun and the earth. Okay, so from this it has to leave. Let's say this is Vs. Now if you use energy conservation, then we can say total energy of this rocket here should be equals to of rocket initially should be equal to total energy of the rocket the final stage. So finally, let's say it is at the infinity, so it will have zero energy, and initially it will be having half m vs square minus potential due to earth, it will be minus g m me by re, right? Okay, and due to sun, so it should be like rs plus re, right? But look, rs is much greater than re, so we'll just write it as rs, so it will be g m ms upon rs. Okay, so this m will get cancelled, of course, so we will be having vs square by 2 equals to g me upon re plus g. Ms is 3 into 10 is to power 5 me upon rs is 2.5 into 10 is to power 4 re, right? So this gme upon re we can take it as common, so it will be 1 plus 10, so it will be 30 and 300 by 25. So if this is this will be 12, right? So this is 13 gme upon re, and vs square into 2, so into 2, and we know this, right? So this is vs root 13 into, we can say, root 2 gme upon re, and this is what, 11.2, so we'll write it as root 13 into 11.2 kilometer per second. So answer will be approximately 40.38 kilometer per second, but in option there was 42, so answer will be 42 kilometer per second. Okay, approximately we have to find. Let's move on to our third question. Third question. So what we have here is a satellite moving with constant velocity v in a circular orbit about the earth. So we have this earth and this is our satellite. Let's say it is at the height h, and this is radius of earth and mass of the satellite has mass m. An object of mass m ejected from the satellite. Okay, so this is actually a satellite, right? And a mass is ejected. So a mass is ejected, and it just escaped the gravitational pull of the earth. At the time of ejection, the kinetic energy of the object is, okay. Let's say the speed is v. So for this ejected object, let's write the energy conservation. So total energy initial is equals to total energy final. So simple, this is quite simple. We have half mv square, right? Okay, so we can write it as okay, let's just use this half mv square. Okay, this is v dash. Let's say this is v dash or v1 we can put. So let's say this is v1. So this is half m v1 square minus g m mass of earth, and the distance from the center will be r plus h, right? So r plus h is equals to, final will be 0 because it just escaped from the gravitational pull of the earth. The gravitational pull of this satellite also we should consider, but we'll just ignore it. Okay, so this is what kinetic energy of the object, and it should be equals to g m me upon r plus h. Now we need GME upon R plus H. Now look, this satellite is revolving around the Earth in this orbit. So if I write the total energy, or we can also write the force equation. Let's write the force equation for the satellite. Force equation for satellite, right? So what we have here, m, the satellite is moving with v square. So this is mass of satellite, v square upon r plus h, right? It will be equals to the gravitational force between them. So it will be g, mass of satellite, mass of earth, okay, upon r plus h to the whole square. So ms will get cancelled, and we have, look, gme upon this r plus h, one r plus h will also get cancelled. We have gme upon r plus h, which is equals to v square. Let's just put it here. So we have simply mv square, right? So this is again quite an easy question. So we have B option is the correct one, right? Let's move on to our third question, fourth question. So this is our fourth question. So 4, 5, and 6, right? We have 4, 5th, and 6th. Okay. So in the fourth question, a geostationary satellite. What is geostationary satellite? The time period of those satellite should be equal to the time period of rotation of the Earth, right? Rotation about its own axis. So it is. So the time period of this satellite will be 24 hours. Okay. In a circular orbit of radius 36,000 kilometer, then the time period of a spy satellite orbiting a few hundred kilometer above the Earth's surface. So, okay, look, situation is like this. This is our Earth, and this we have is the path of the, okay, and we have another satellite. So let's just make this, okay. So I'm just write this. Okay. So look, we have a satellite here. This is our geostationary satellite. Okay. And we have a satellite here. This is a spy satellite. It's few hundred kilometers, so we'll just approximate it that it is just near the radius of the Earth. Okay. Now both are revolving around this axis. So if this axis is passing into the plane and towards you, right? So this is axis. Of course, they are revolving around the Earth. So we can use Kepler's law, right? Okay, perfect. So we will have T1 square upon T2 square will be equals to R1 square upon R2 square. We know this, let's say this is geostationary and this is the spy one, okay? So this is the radius, I mean the distance from the axis G, and this is the distance of the spy satellite from the center of the Earth, right? So around the Earth in a circular orbit of radius 36,000. So this TG is, it will be 24 square upon TS square we have to find, and RG will be 36,000. Oh, so this will be the cube, right? 36,000 cube upon RS, and RS will be, we'll just take it as radius of Earth, so it will be 6400, right? So if you cancel it without expanding it, so we will be having 36,000 upon 6400 whole cube and 24 square upon ts square. So these two zeros will get cancelled. We can cancel it out with the 8, right? So this will be 8. So we will have 8 4, 8 into 4 32, so 4, and this will be 45. Okay. So simple will have Ts square will be 24 into 24 into 8 cube upon 45 cube, right? 45 cube. Okay. So I'll just use the calculator really fast. So we will be having 24 into 24 into 8 cube divided by 45 cube. So we have, this will be 3.236. Okay, but this is t square. So what we have to find here, ts will be the root of this 3.236. So what we will get, 236 will get approximately 1.78. Okay, 1.78 will be 2 hours. So C will be the option, right? So quite easy question, but look, in this this is the only problem with the gravitation chapter, that the calculation will be lengthy. Okay, so we can't do anything here. Let's move on to our fifth question. So we have, right, an artificial satellite moving in a circular orbit around the Earth has a total energy E naught. So right, we have E naught. And what was it? It is, let's say, minus x. Then kinetic energy will be x and potential energy will be minus 2x, right? It's potential energy. So if minus x is E naught, so we'll write it as 2 minus x. And minus x is E naught, so potential energy will turn out to be 2 E naught, right? So 2 E naught. C will be the option. That's easy, right? Let's move on to our sixth question. Let's move on to our sixth question. Okay, what we have here is two bodies, each of mass m, are kept fixed with a separation 2l. Okay, the particle of mass m is projected from the midpoint of the line joining the other two centers perpendicular to the line. So look, we have two bodies, okay, and this is the line joining the center, and this line is of the length 2l. Okay, now there is this particle, this is m, this is capital M, this is capital M, and it is given a velocity v in this direction, let's say, right? So the correct statement is or R. We'll check the statements. So we have these are the statements, right? So this. So one statement is minimum initial velocity, initial velocity. Okay, so in this we have to find the escape velocity, right? Because to escape. Okay. And the third is the mass energy of the mass m remains constant, right? Yes, and this is what we are going to use here, right? So let's conserve the total energy. So total energy, so this option is correct, right? So total energy initial of mass small m will be equal to total energy final of mass small m. So initial energy we have, it will have is half mv square, and the gravitation potential due to this and this on this. So we'll have minus gm capital M divided by this is L, right? And due to this, the gravitation will be same again. Okay, and finally it will have zero energy. So we'll have half small mv square will be equals to 2g small m upon capital M upon L. So m will get cancelled and this will be 2. So it will be 2 root g m by L. So B option is correct. Okay, so quite easy question again. So B and D will be the answers, right? Let's move on to our seventh question. So this is our seventh question. We have, let me enlarge this image a little bit. Okay, so right, we have two spherical planets. P and Q have same uniform density and the mass this and this. Surface area A and 4A, the spherical planet R also has uniform density rho, okay, but its mass is this. So escape velocities we have to, okay, okay. So let's make the diagrams first. Let's say this is P, this is Q, and this is let's say R. Now the mass of planet is MP, okay, and they have surface area, okay, this is MQ and this is MR, which is MP plus MQ. They both have same uniform charge density, so this is rho, uniform mass density, so the rho, okay. But the surface area of P and Q is such that A and 4A. So let's say the surface area is A. So we have the formula for A is 4 pi r square. So it's 4A. So how it will come? So this its radius must be twice. So let's say its radius is r, then its radius will be 2r. Right? Now we can also compare the masses here because density is same. So its density will be mp upon 4 by 3 pi r cube, and its density will be mq upon 4 by 3 pi 2r cube, and both are same, right? So mp will be equals to mq upon 8. So if we say mq is m, or we can say mp is m, right? Let's just consider this. So let's say mp is m, so it will be 8m, right? And this will be 8 and this will be 9m. Okay, perfect. Now, do we have everything? No, it's radius. So we don't know the radius here. So, okay, let's just consider this smaller. Otherwise, we might get confused here. Perfect. Okay, its radius we don't know, but it has uniform density rho. So its density is also rho. So we can find the radius. So it will be, so we'll just compare it with this. So we have density of P equals to density of R. So density of P will be m upon 4 by 3 pi R cube is equals to, it will be 9m upon 4 by 3 pi R dash cube. So this m will get cancelled and we have 1 upon R cube will be equal to 9 upon R dash cube. So R dash will be R 9 to the power 1 by 3. Okay, right. So we have its radius also we, right? Now just we have to find the escape velocity for all three. So escape velocity of Vp will be simply, it will be root 2 g m upon r. Vq will be root 2 g mq. Mq is 8m upon rq. Rq is 2r. So this was small r, right? This was small r. Okay. So this was small r, right? So 2 will get cancelled. So it will be, look, we'll have, this is 4. So 4 to 2 gm by r, right? So this will be 2 Vp because this is Vp, right? So we'll have 2 Vp. This 4 will come out. Okay. And now Vr. So Vr will be root 2 g. Mass is 9m upon radius is r, 9 to the power 1 by 3. Okay, so this will go up and we'll have 9 to the power 2 by 3 root 2 gm by r, right? So this 9 will go up. So this was 1 minus 1 by 3. This will be 2 by 3. And you have to take the root. So we'll get 9 to the power 1 by 3 into Vp. This was Vp. Okay, right. So clearly Vp by Vq is 1 by 2. So D option is correct, right? Mm, and look, this 9, so it will be more than 8. 9 is what? More than 8, right? So this will be greater than 2 Vp. So Vr is greater than Vq, Vq, right? And Vq is greater than, of course, V. So B will also, right? So we'll have B and D as our answer, right? So it's easy. We don't have to solve this 9 to the power 1 by 3. Okay. Well, simply, if this was it, then this will be 2 Vp, right? But it is 9. So the answer will be greater than 2 times of Vp. So simple. Let's move on to our, this was 7th. So this must be our 8th. Okay. So this is our 8th question. We have a satellite moving in elliptical orbit around the Earth. The mass of the satellite is very small compared to the mass of Earth. The acceleration is directly towards the center, correct? Angular momentum of S about the center of the Earth changes its direction. No, of course, the angular momentum is constant. The total mechanical energy S varies periodically. Wrong. The total mechanical energy is also constant. Linear momentum of S remains constant in magnitude. No. Look, if it is moving in elliptical path, velocity velocity will change. How? The magnitude will change, right? As well as the direction of this velocity also changes. Okay, so both will change. So linear momentum's magnitude will not remain constant. So this is wrong. So only A will be the option. Okay. Sorry. Let's move on to our ninth question. Excuse me. Okay. This is our ninth question. So we have two spherical stars A and B have density rho A and rho B. A and B have same radius. So let's make a diagram. So we have this is A and this is B. They have same radius, so we'll just consider it as R. And the mass of A and B are related like this. So MB is 2. So let's just write it as 2M and this is M. Okay. Due to interaction process, star A loses some of its mass so that its radius is half. Okay, so what happens is after a situation, what happens? This becomes, let's say, A. Okay, now the radius becomes R by 2, right? Spherical shape is retained and its density remains same. So let's say the density of this is a rho. So density is same, right? So we will just write if the density is same and we have density is mass upon volume. So it will be 4 by 3 pi r by 2 to the whole cube. If density is same, the mass should be 1 by 8 times, right? So its new mass will be m by 8. Then the 2 factor will get cancelled and we'll have the same, okay? So I'm just directly writing it like this. We can solve it, of course, but I'm just directly writing it up. And the entire mass lost by A is deposited as a thick spherical shell on B with the density rho. Okay. So what happens is this was our B, this was our B, right? What happens is this mass which is lost from A is deposited around B like this, right? So this is, and the density, what happens is density of this part remains same, right? So this is the radius R and this radius is actually, let's say it is r dash. If v and vb are escape velocity from a and b after the interaction process, so this is after they're talking about. So we need r dash, then we can solve this question, right? Okay, let's find the r dash first. Mm, so how will write? So we will just write this volume, right? We have this mass. So the mass of shaded region. So what will the mass of shaded region? Look, this one has a mass m and left we have left with m by 8. So this mass will be 7m by 8. It should be equals to density of this part into the volume. So volume will be this whole volume minus this. So we'll have 4 by 3 pi r dash cube minus 4 by 3 pi r cube, right? Okay. So this we have, and the density will be simply, so let's just write it 7 by 8 m, and the density will be m upon 4 by 3 pi r cube. So m upon 4 by 3 pi r cube, 4 by 3 pi r dash cube minus 4 by 3 pi r cube, right? So 4 by 3 will get cancelled. If we take this common, m also cancel. So we'll have 7 r cube by 8 is equals to r dash cube minus r cube. So this will go here. This is r dash, right? So we have r dash cube will be equals to r cube plus this. So it will be 15 by 8 r cube. So we have r dash as 15 to the power 1 by 3 r, and this divided by 2. So we got the r dash, right? Now we'll just write the escape velocity for these. Okay, so let's just write the escape velocity. So we have VA. So VA after the interaction process we are talking about. So it will be 2g, m will be m by 8 upon radius will be r by 2. So we have, so this will be the 4 and 2. We'll get g m by 2r, right? So 4 divided by 2 or 4 divided by 8, so it will be 1 by 2, right? So this is VA. Now let's find VB. Okay, so I'm writing VB here. So VB will be what? Okay, now look, the escape velocity is from the outside. Okay, we'll just, and this whole is a sphere. Okay, so if you conserve the energy, we just have to write the total mass. So what it will be? It will be root g total mass of the sphere after the interaction process 2g mt by radius, which will be r dash. So we'll just write it as 2 into g m total. The total m is what? So it was initial 2m and final it will be 7m by 8. So this whole we have to add. So let me write mass, total mass will be, it will be 2m plus 7m by 8. So it into 2 16 plus 7 will be 23m by 8, right? So we'll just write it as 23m by 8, and r dash was this. So let's just put it over here. So we have p 15 1 by 3 and 2 will go here, and r is like this. So this will get cancelled and it will be 4, right? Now let's just divide both of them. Let's just divide this and this. Okay, so we get VA upon VB upon VA will be root everything in this root, right? So it will be 23 gm by 4, 15 to the power 1 by 3, and the r will be here like this. Okay, and VA will be gm upon 2r. Okay, so this 2 and this 2 will get, so it will be 2, right? So this will be 2. not 4. So R2 GM will get cancelled. Simply we have root 23 by 15 to the power 1 by 3. This is 10. So if you multiply it by 10 and 10, we'll get 2.3, right? So this was quite easy, but our calculation is a bit lengthy, right? So it was easy. Let's move on to question number 10. So we have these questions now. Okay, perfect. Right. So in the 13th question, we have the distance between two stars, 3M and 6M, is 9R. So this is a star, its mass is 3ms. This is a second star, its mass is 6ms. And the distance between them is 9R. Okay. R is the mean distance between the center of the earth and the between the centers of the earth and the sun. So look, if this is our sun and this is our earth, right? And this is the mean distance, because we'll consider, if we are talking about a mean distance, right? Then we can consider it as a circle. So this is R, right? Perfect. Ms is the mass of the sun. Okay. The two star orbit around their common center of mass in the circular orbit with a period nt. T is the period. Okay. So we have so the T is the period of Earth around the sun. So we have T as 2 pi r cube. I mean root r cube upon g mass of sun. Right. Okay. So they are also moving, and we know if they're moving about their center of mass, and we can also find the center of mass, right? So if it is an 9r and this is 3ms and this is 9ms, so what will be what the center of mass, where the center of mass will be? So it will be 6r from this and 3r from the mass whose the star whose mass is more, right? And they are moving like this. So this will be moving about this, so its path will be like this, right? And path of this will be like this, right? And we know though both of them will have the same time period, right? So we just need to find the time period of only one. Let's start. So we'll make the will this is our 3ms. Let's make the diagram. This is the center about which is it rotating 6r. So we'll write the force equation first. So we will have the gravitation force will be equals to mv square by this 6r, right? So Fg will be G 3ms into 6ms upon the force between them. It will be 9r to the whole square. And this will be ms. It will be 3ms. So 3ms. So this will be 3ms v square. Of course, this is the smaller one. Let's just say it is the smaller one. So this is the velocity of the smaller one upon 6r, right? So 3ms will get cancelled, and we have this will go here. So we have g 6 square ms, and one r will get cancelled, right? So we have 9 square upon r. This will be velocity of smaller one. Okay, and it will be the root. So let's just make it the root like this. Now we know the time period will be 2 pi r, which will be 6r upon v. So we'll just put this So it will be 6r, and v will be root. So this 6 will come out, right? This will come out. So it will be 6 upon 9 g ms upon r, right? Perfect. So we have time period will be this 6 will get cancelled, 9 will go up, and we have 2 pi root, this will go inside. So yes, it will be r cube upon gms, right? And this was the time period of Earth. This was the time period of Earth. So we have n as 9 because this n we have to find. So n will be 9, right? So again, it's quite easy question, of course. Just we have to solve some equation, force equation I have applied, then find the time period. It's quite an easy question, right? Let's move on to our 11th question. Let's move on to our 11th question. So we have a bullet fired vertically upward with a velocity v from the surface of a spherical planet. When it reaches its maximum height, the acceleration due to gravitation planet is 1 by 4th of its value. If the escape velocity from the planet is this, find the value of n. Okay, so look, it is thrown upward with the speed v, and what happens is when it reaches the maximum height, means velocity is 0. Let's say it is h. The gravitation g here, g dash will be g by 4. Okay, so let's use the energy conservation. So total energy initial is equals to total energy final. So initial we have half mv square minus g m capital M. Let's say this is the planet whose mass is m upon capital R and its radius is capital. Be equal to final energy will be minus g small m capital M upon R plus h. Right? A bullet is fired with a v. Its value is the escape velocity from the planet is this. So we can put this quantity here, right? So v will be v escape velocity divided by root n. Okay. Let's find h first because we don't know this v we have to find from this equation, but we don't know h. So let's find h first. Let's use this information. So gravity is 1 by 4th of its value at the surface. So let's find the g dash. So g dash will be, yes, it will be g upon 1 plus h by r the whole square, right? It will be g by 4. So we have 1 plus h by r is equals to 2 because I have taken the root. So we have h by r is equals to 1. So h will be r, right? Let's put these values here now. So this m will get cancelled. So we have half v square will be equals to, this will go here. So gm by r minus gm by 2r. So we have half v square equals to gm by 2r, right? 1 minus 1 by 2 is 1 by 2. This will get cancelled. So we have v as root gm by r. Okay, and we know the escape velocity is root 2 gm by r, right? So we have, if you put those values, so this will be equals to root 2 times of v. So we have n as, okay, if you put this equation and will come out to be 2. So again, quite easy question, right? Let's move on to our next question. So yes, this will be our 12th question. So this will be our 12th question. So what we have here is a binary star consists of two stars, thus this, where m is mass of sun, they are separated by distance d, and are rotating about their center of mass, which is stationary. the ratio of total angular momentum of binary star to the angular momentum of B about their center. Okay, so we'll use the concept again. If they're rotating about their center of mass, let's just make the diagram. So this, let's say the star whose mass is 11 ms, and this is the smaller one. Its mass is 2.2 ms. Okay, and this is the line joining them. Then center of mass will be here, and this distance will come out to be, if this hole is d, right? This whole distance is d, then this will be what? It will be 2.2 d by total of these mass. So it will be 13.2, right? And this distance will come out to be 11 d by 13.2, right? Okay, and we know, but in the binary star system, the time period of both will be the same. So if time period is the same, then let's say this is the star A. Okay, so this is star A, this is star B. So omega of A must be equal to omega of B, right? So let's write the total angular momentum of the system. So total angular momentum will be ma ra. Okay, so this will be ra, and this will be rp. So ra omega square plus mb rb omega square. Omega is same, so I'm just considering it as omega, and we have to divide it by angular momentum of b. So it will be mb rb omega square. So omega square will get cancelled. So let's put those values. Ma is what? 2.2 ms. Ra. Ra will be 11 d by 13.2. Okay, plus mb will be 11 ms into rb. So rb will be 2.2 d divided by 13.2, and then divide both them with by mbrb. So mb will be 11 ms into rb is 2.2 d by 13.2. So a lot of things will get cancelled. md msd will get cancelled, 13.2 will get cancelled. So we are left with 2.2 into 11. I've done some mistake, I think. So angular momentum is m r square omega. Okay, so that was a big mistake. Let me correct it. So it will be mr square omega. Okay, yes. So this will be square. This will be square. So no worries, the d and 13.2 square will also get cancelled. So we are left with 2.2 into 11 into 11 plus 11 into 2.2 into 2.2 divided by 11 into 2.2 into 2.2. So look, 111 will get cancelled and 2.2 will get cancelled. So we are left with 11 plus 2.2 will be 22 by 10, right? So let's just write 2.2 upon 2.2, right? So we will have this 11 will, if you take 11 common, so we'll have 11 into 1 plus 2 by 10, and this will be 11 into 2 by 10. So this will get cancelled, so it will be 12 upon 2. So it will be 12 upon 2, right? Okay, 12 upon 2, right? So everything is correct, right? We will have 6 is the answer. Okay, right? So answer will be 6. Okay, so it was quite easy. Again, remember this concept. If two stars or two systems are rotating due to their mutual gravitation, then time period will be the same. Okay, right? So let's move on to our 13th question. We have gravitational acceleration on the surface of a planet is root g by 11 into 6, right? So let me take this part on the downside. Okay, let me adjust this. So right. Okay, so this was our 13th question. So we have a planet whose gravitational acceleration is this, and average density is this. If the escape speed of the surface of the planet is taken on the Earth is taken to be this. Okay, so we have, let's say, the planet whose acceleration due to gravity is gp, so it will be root g by 11 to g. Okay, root 6 by 11 into g. Now the average mass density of the planet is 2 by 3 times of Earth, so density of the planet will be 2 by 3 times of density, right? So we have to find the escape velocity, right? So escape velocity of the surface of the planet will be perfect. So we have to find vp, so it will be root g, 2 g at of the planet and r of the planet, right? So we can just write it as, if you put those values, so 2 into gp will be root 6 by 11 r, g of earth, of course. This is g of earth, right? Into r of planet we need. Now for that, let's see what is this. So gp will be gmp upon rp square will be equal to root 6 by 11, and this will be gm upon r square. And what is this? So it will be density of planet. It will be mass of planet upon 4 by 3 pi rp cube will be equals to 2 by 3 mass of earth is 4 by 3 pi r cube. So look, if you divide this by this, then rp square and 1 r 2 rp square will get cancelled. We'll left with rp, and mp will get cancelled. So let's just divide these two. So let's say this is 1, this is 2. If we divide, we'll get this rp will go up. So rp will be equal to root 6 by 11 into 2 into 3 into, and this r will go up. So this will get directly if we divide these two. So let's just put this value in this. Let's put this value in this, and we will get Vp as root 2 into root 6 by 11 G. Okay. So let me write it in the next line, right? So Vp will be root 2 into root 6 by 11 G into Rp is root 6 into 3 by 11 into 2 R. Okay. So what we have here is root 2 GR. Let me remove this part. Root 2 G and R. Other things will be root 6 into root 6 will be 6 into 3 divided by 11 square. So 11 square into 2. So this will be 3. So we have 9 by 11 left. So 9 by 11, and root 2 GR is given. It will be, we have to take it as 11. So we will have 9 kilometer per second. This is the escape velocity of the planet, right? So it's simple. Look, if you try to find the radius, then just divide these two, you will get the radius of the planet, right? So answer will be 9, right? Okay, 3 will come. Oh, okay. So this will be 3. It is 3 square, right? So answer will be 3, right? Answer will be 3. So this will be 3 by 11. and 11 will get cancelled. So we'll have 3 as the answer. So this is 3 kilometer per second. Okay, let's move on to our 14th question. So we have our 14th question. This is our 14th. A planet of mass m has two natural satellites with mass m1 and m2 and radius r1 and r2 respectively. Ignore the gravitation between these is. So this is quite easy, right? V1, L1, K1, T. Okay, so there must be something. Let me add this part. So right. Let me expand that a little bit. Okay. So now this wasn't the part. Okay. Let me get the options. So it was match the following. Okay. So we have to compare V1 with V2, L2, L1, K1 and K2 and T1 and T2. We have to compare them. Let's compare. So look, we have this planet and this is the first satellite and this is our second satellite, right? This is our satellite 2. This is 1, right? Okay, perfect. Now the ratio of this is given in the question. So it is R1 by R2 is 1 by 4. Okay. And M1 by M2 is also given. It is 2. So we have to compare V1 by V1 and V2, L1 and L2 like this, right? So let's compare. Okay. So let's first compare uh, time, right? So we know if uh, two planet satellites are revolving around orbit with the same like axis of rotation, right? So time period will be proportional to r cube. Kepler's law, t square will be proportional to r cube. So we have t1 square by t2 square will be equal to r1 cube upon r2 cube. So r1 by r2 is 1 by 4 to the whole cube, and this t1 by t2 we have to write 3 2 by 3. So this will be 1 by 8, right? So I can show you this. Can show this to you also. So we have 1 by 2 the whole square into 3 by 2. So this 2 will get cancelled and simply will get 1 by 8. Right? So this will be the T1 by T ratio of T1 by T2. Okay. What else we can find? We can also find V1 by V2. So V1 by V2 is what? So it will be omega 1 R1 by omega 2 R2. Omega 1 by omega 2 will be, so it will be T2 by T1, right? Into R1 by R2. So our T2 by T1 will be 8 and R1 by R2 is 1 by 4. So this will get cancelled. We'll have to. So this is how we have to compare all those things. Yes. So it's quite easy, right? Okay. So let's move on to our, this was our 14th. Let's move on to our 15th question. So let's move on to our 15th question. So right, these are our questions. Okay, perfect. So we have a question statement question. So in the statement one, an astronaut in an orbiting space station above the Earth experienced weightlessness, right? So this is correct. An object moving around the Earth under the influence of Earth gravitational force is in state of free fall. Yes, this is the condition for free fall. Even we are in the free fall. But what is happening is we have downward is a mg, but we have a normal. So that is why normal is actually balancing mg. So we say like we are not falling, we are at rest. Okay, but like if you throw a particle from a height, then it will have only mg and we'll consider it as a free fall. So this is a correct explanation, so it will be the answer, right? So this is a class ninth question actually. Let's move on to the 16th question. So we have a body is projected vertically upwards from the bottom of a crater of the moon of a depth r by 100. Okay, where r is the radius of the moon with the velocity equal to escape velocity on the surface of the earth, right? So we have the planet or moon, you can say, and this is the depth from which a particle is thrown, right? This depth is r by 100. Okay, so this will be the center. This is r, and the mass of this planet is m, right? And it is thrown with the escape velocity, but it will not escape, right? Because it is at the depth. If it was thrown from the surface, then it will have escape, but now it will not escape, right? Or we can look if like final energy will come out to be zero, then we'll say it will escape. Otherwise, it will not. Okay, perfect. So, and in the question, it is also asking calculate the maximum height attained by the body. So this h we have to find. Let's say it will reach here. Okay. So let's say it will reach here, and this h we have to find. Okay. So again, we can write total energy. Initial total energy will be equals to final total energy, right? Let's write. So initial total energy, it will be half m vs square minus. Now we have to write the potential at A. Okay, it will be final will be it will come out, it will be at rest here, right? So velocity at here will be zero. So the potential will be minus g. So let's just write this as a VA minus g small m capital M by r plus h. Now VA we have to write. Just think for a second how we'll write VA. This is the first question we're discussing where we have to write the potential inside the moon, right? Just think for a second what will be the potential at a depth r by 100, right? So look, if you remember, let me write here. If you remember, we have solved this in the electrostatics, right? So if this is a sphere whose charge density is anything, let's say its total charge is q, radius is r. So at this point from the center at a distance small r, we have the potential at A will be kq by 2r, right? Into 3 minus small r square by capital R square. This is exactly we are going to use here. Okay. So let's use, so it will be half mvs square minus, so of course minus will come, right? Because look, the potential increases in the direction, potential decreases in the direction of field, so field will always be in the downward direction. So if you write it here, the field will decrease because at infinity we are taking it as a zero, so here it will be negative. It will be minus, in the place of k we'll write g, in the place of q we'll write the mass of planet. Okay, and if this is va, of course if we multiply it by mass of the charge of the a small charge q, then we can find the potentiality. So it will be small m capital M divided by 2, and this is small, this will be capital R, right? It will be capital R. So where capital R is this, into 3 minus small r will be the distance from the center. Okay, so this distance we have to take. So it will be 99 r by 100. So it will be 99 r by 100, and this will be square into 1 by r square. Okay, so calculation will be a little bit complicated. We have this will be minus g small m capital M upon r plus h. So this small m will get cancelled. We have vs square upon 2 will be equals to uh, if you take it here, it will be plus, so it will be g m by 2r. We have 3 minus 99 square, so 99 square, I'll use the calculator really fast. It will be 9801 and divide by 100, so it will be 9, so 100 square, so it will be 0.98, and r square will get cancelled, minus g m by r plus h, right? So let's just uh, let it remain in on the left side. Okay, because we have to put the value of vs, so let's put the value of vs. It will be root 2 gm by r, so square will be 2 gm by r, and this will be 2, 2 will get cancelled, and if you take gm by r common, we'll have 1 minus 1 minus, so let me rub this, so we have 1 minus 1 by 2, and 3 minus 0.98, so 3 minus 0.98 will be 2.02, right? So it will be 2.02, right? It will be equals to minus gm by r plus h, right? So gm will get cancelled, and we have this will be 1.01, so it will be 1 by r. 1 minus 1.01 will be minus 1 by r plus h. So if you solve, we'll get it will be minus 0.01 by r is equals to minus 1 upon r plus h. So minus will get cancelled. We'll have 100r is equals to r plus h. So it will be 99r equals to h. Okay. So calculation will be a bit complicated, but the solution is easy, right? This is the problem with this chapter. Okay. So we have the maximum height it will attain will be 99 times of r, right? So this was our 16th question. Let's move on to our 17th question. This is 17, this will be 18, and this will be 19. So let me write the 17 here. So we have artificial satellite is moving in a circular orbit around the earth with the speed half equal to half the magnitude of escape velocity. Determine the height. So this is a quite easy question. The velocity here is vs by 2, so right, we have to find the height, and it is moving in a circular orbit like this, so let's say this is h. So we knew the total energy will be negative of half m v square, so it will be minus half m, and v will be 2 g m by r, right? Because this is okay. So let me put the value, otherwise do some mistake here. Okay, so v is what, vs by 2, so vs by 4. Okay, let's put the values, minus half m, and vs square will be gm by 2gm by r, and this will be 4, right? Perfect. And the total energy at a height h will be will be what? The total energy will be, it will be half of potential energy, right? So potential energy will be minus G M, capital M, divided by H plus R, and it will be the half of this. So this is the total potential energy, and we have to take it. So minus half will get cancelled. G M M will get cancelled, and we have 1 by H plus R will be equals to 1 by 4R. So simply H will be 3R, right? So H will be 3R when the height of the satellite above the Earth surface, right? We have done mistake, any mistake? Mm. Oh, this 2 is left, right? So it will be 2. So this will be 2R. So we have R. So H will be equals to R, right? Yeah, that was the answer. Okay, so H will be R. Okay, so quite easy question. If the satellite stops suddenly in its orbit and allowed to fall freely onto the Earth, find the speed with which it hits the surface of the Earth. So again, an easy question. So look, this is our Earth, right? And the particle is at here, and this H is R. So we can write initial total energy equal to final. So total energy initial equals to, this is the final point, right? Total energy final. Okay. So we have initial energy will be minus G M M by 2R. This is the potential energy. And the final energy will come out to be, it will be minus G M capital M upon R plus half M V square. So this we have to find. So this will come here. This is 1 minus 1 by 2. So it will be 1 by 2. So G M by 2R will be equals to half M V square. So this M will get cancelled. This 2 will also cancel. So V will be root G M by capital R. Okay. So this is quite easy. Let's move on to 18th question. So 18th question. What we have here is two satellites S1 and S2 revolve around the planet in a coplanar circular orbit in the same sense. Okay. So we have this planet, right? We have one satellite like moving like this, and we have another satellite moving like this, right? So let's say this is the first satellite, this is the second. The time period is given and the radius of S1 is given. So let's say this is S1, this is S2. So we know T1 square by T2 square will be R1 cube upon R2 cube. So T1 square is what? It will be 1 square upon 8 square, and R1 is 10 raised to power 4 to the whole cube upon R2 cube, right? So we have R2 cube will be equals to 10 raised to power, this will be 12 into 64. So R2 will be 10 raised to power 4 into 64 to the power 1 by 3. So it will be 4, right? So we'll have 4 into 10 raised to power 4. This will be R2. So we got the R2. Okay. What we have to find? We have to find the speed of S2 related to S1 when it is S2 is closest to S1. So this will be the closest. So let's say this is moving with V2, this is V1. So velocity of 2 with respect to 1 will be V2 minus V1. We'll just subtract it. So V2 will be what? So we have to find the V2 first. Let's find them. So V1 will be, it will be 2 pi R1 upon T1. So 2 pi R1 is what? 10 raised to power 4, and T1 is what? 1. So we will have 2 pi 10 raised into 10 raised to power 4 kilometer per second. And V2 will be like this. So it will be again 2 pi r2. R2 is 4 into 10 raised to power 4 divided by T2 is 8. So this will be 2. This 2 will get cancelled. So it will be pi into 10 raised to power 4. So we will have 2 pi into 10 raised to power 4 minus pi into 10 raised to power 4. So this will be 2 minus 1. So it will be pi into 10 raised to power 4 kilometer per hour. So this is V21. Okay. So this is A. Now the second we have to find the angular speed of S2 as actually observed by an astronaut on in S1 and when it is S2 is closest to S1. Okay. Now we know the formula for relative angular velocity is omega 2 minus omega 1, but this is incorrect. Why? Look, if S1 is here and S2 is here, okay, as they're moving, the angular velocity will change. But at this point, we have to find. So we have to take this V21 and this is R21. So this will be our omega of S2 with respect to S1 at this moment. So omega 21 will be V21 upon R21. This formula was correct. But in this context, right, when they're closest, it is moving with V21. Okay, and the distance between them is R21. So this we have to use. So V21 we have calculated pi into 10 raised to power 4 divided by. Okay, so this will come out to be V21. It will be pi minus 2. So this will be negative. Of course, it will be negative, right? Okay, so V1 will be moving a bit faster, right? Compared to perfect. So V2 will be this upon R21. So R21 will be 4 into 10 raised to power 4 minus R1 was 10 raised to power 4. Okay, so we will have pi into 10 raised to power 4 upon 3 into 10 raised to power 4. So this will also get cancelled. And pi is approximately what? 3.14. So it will be 1 point something. So we can just say it's 1, right? Okay. Uh, the radius, right? So this was in kilometer per hour. This was, so this will be almost pi upon 3. It will be radian per hour. Okay. So if you want to calculate in second, so we will have omega 2 will be pi by 3 and r will be 60 into 60, right? So if I use a calculator really fast again, divide by 3 divided by 3,600. So we have approximately 0.0003. So it will be 3 into 10 raised to power minus 4 radian per second. Okay. So this was the important concept here. So it's quite a nice question. Okay. Now next, it is possible to put an artificial satellite into an orbit in such a way that it will always remain directly over the New Delhi. So this is a question where you should know the position of New Delhi. So it is not on the equatorial plane, right? That is why you cannot, if you like, if the New Delhi was on the equatorial plane, then it will remain there. The satellite will always. But New Delhi is not on the equatorial plane, so this will be the false. Okay, so let's move on to our 20th question. So we have this. Okay, so in this question, we have two masses, the masses and the radii of the Earth and Moon are this. Okay. The center are at a distance d apart. The minimum speed with which a particle of mass m should be projected from the point midway between two centers so as to escape to infinity. Okay. So again, this question is similar to what we have discussed before. So let's put it like this. So this is M1 R1 and this is M2 R2, right? And this they are d meter apart. So we have put a particle of mass m in the middle. So what we have given it as a velocity v. So it will have half. Again, we have to conserve the energy. Total energy initial equal to total energy final. So initial total energy will be half mv square minus potential energy will be g m1 small m by d by 2 minus g m2 small m by d by 2 will be equals to, and the final energy will be 0. So simple, small m will get cancelled and we have v square by 2 equals to 2g by d m1 plus m2. So we have v as root 2 to 4 g m1 plus m2 by d. Okay. So again, this is a similar question we have just discussed. Let's move on to our final question. So yes, we have a geostationary satellite orbiting the Earth at a height 6 by 6r. So we have this as a geostationary satellite. This is 6r and this is r, right? So it will be at 7r. The time period of another satellite at a height 2.5. So it will be, so we will use the same Kepler's law. T1 square by T2 square will be R1 square cube upon R2 cube. Now T1 square, so this is geostationary, so it will be 24 square upon T2 square will be equal to R1 square. So R1 will be 6R plus R, so it will be 7R cube, and R2 square will be 2.5 plus this, so it will be 3.5. So T2 square will be 24 into 24 and into 35 into 35 into 35 divided by 1000, right? And this will be 7R and RR will get cancelled, right? So it will be 7 into 7 into 7, right? So this will be 5, 5 and 5. And this will be 2, 2 and 2. So this will be 8. And this is 3, right? So T2 will be 24 into the it will be 72 root 72 we have to find. So near to it is 64. So 8 point answer is 8.48 hours approximately. So this will be the answer, right? So this was our final question. As you can see in the chapter gravitation, in the chapter gravitation, the concepts are very limited. So we have limited concepts. Okay. And overall the questions are easy, not even moderate. Okay. So always try to attempt those questions. And of course, gravitation is similar to our chapter electrostatics from class 12th, right? It is similar to our chapter, right? Electrostatics. So rather than gravitation, try to focus more on electrostatics. Okay, give less time to this, give less time, because the questions are very limited in the JEE Advanced. So give less time and focus more on electrostatics. Okay, on electrostatics. So this is like the crux of this chapter. Let's finish the video.